Photons streak across the void, racing from Earth at a speed that feels infinite, yet still requires over 4 years just to touch the surface of our nearest stellar companion. At this velocity, traversing the full width of our galaxy becomes a voyage measured not in human lifetimes, but in epochs spanning 100 millennia. We find ourselves confined within an invisible cage, imprisoned behind barriers constructed not from steel or stone, but from the fundamental laws of physics themselves. Yet what if these ironclad laws could be made to yield? What if the bars of our cosmic cell could simply warp and bend? Scientists have discovered a mechanism capable of propelling spacecraft at velocities 10 times greater than light itself, transforming journeys that would consume entire centuries into expeditions lasting mere decades. You are about to explore warp bubbles manifesting in controlled laboratory environments, gravitational ripples concealing the signatures of alien vessels, and energy demands plummeting from mathematically impossible to merely extraordinarily challenging. The breakthrough humanity has been waiting for may already be unfolding in research facilities scattered across the globe. Our story begins with understanding exactly why we are trapped and why escape has seemed so utterly impossible for so long. The fastest machine humanity has ever constructed, the Parker Solar Probe, tears through space at velocities approaching 190,000 miles every hour. The number sounds extraordinary until you confront the sobering reality that even this record-breaking spacecraft would require 70,000 years to complete a journey to our closest neighboring star. Such a voyage would commence during Earth's last ice age and conclude in a future so distant our current civilization would be ancient history. We remain caught in a velocity trap from which conventional rockets offer absolutely no liberation. Light itself travels at an astonishing 670 million miles per hour, and even this cosmic speed limit demands 4.5 years to bridge the chasm separating us from Proxima Centauri. Our galaxy stretches across a distance of 100,000 light-years from edge to edge. Calculate these numbers honestly and the conclusion becomes inescapable. Crossing our own galaxy transforms into an odyssey spanning thousands upon thousands of years. Every distant sun you observe glittering in the darkness of night represents a destination that existing technology renders completely unreachable within any single human lifespan or even within the span of many consecutive lifetimes. The Voyager probes, launched back in 1977, have now traveled barely 14 billion miles from their starting point. Nearly 5 full decades have elapsed since these machines began their journey into the cosmos. Despite this tremendous passage of time, they have not yet completely escaped the gravitational embrace of our own solar system. The stars beyond remain separated from us by distances so impossibly vast they might as well be located in another universe entirely. We are cosmic children still learning to crawl when the situation desperately demands that we learn to run at speeds that defy comprehension. Space extends beyond mere bigness. It actively ridicules our grandest ambitions. The gulfs between stars stretch so enormously that even traveling at 99% of light speed would transform interstellar missions into commitments spanning multiple human generations. Your descendants, many times removed, might eventually witness the destination you originally aimed toward. Every propulsion mechanism we have successfully engineered operates according to the identical basic principle that has governed rocketry since its inception. Expel mass violently from the rear to generate forward momentum. Chemical rockets accomplish this through controlled explosions. Ion drives achieve it by accelerating electrically charged particles. Nuclear engines blast superheated gas at extreme velocities. All of these systems obey the familiar laws of classical physics, and all of them move with agonizing slowness when compared against the cosmic distances we need to traverse. Scientists have labeled this fundamental limitation the tyranny of the rocket equation, a mathematical prison from which there appears to be no conventional escape. The underlying problem manifests with brutal clarity. The greater the quantity of fuel you carry, the more massive your spacecraft becomes. The more massive your spacecraft, the larger the quantity of fuel required to accelerate it. This vicious cycle spirals into a nightmare where fuel storage tanks grow to dwarf entire metropolitan areas just to achieve a minuscule fraction of light speed. Adding additional thrust capacity merely compounds the weight problem further. We have successfully dispatched robotic explorers to Mars, landed sophisticated rovers on distant moons, and captured photographs depicting the uttermost edge of our observable universe. Yet despite these remarkable achievements, we remain trapped within our own immediate neighborhood. staring longingly at boundaries we lack the capability to cross. The nearest world that might potentially support human habitation sits just 4 light-years distant. Reaching it using current propulsion technology would demand an uninterrupted flight lasting 25,000 years. Something fundamental must change. The cosmos overflows with billions of potentially habitable planets scattered throughout the galaxy. Yet our technological limitations mean we can scarcely reach the nearest lifeless rock in our immediate vicinity. The question that haunts every physicist working on this problem becomes obvious. What force keeps us chained so tightly to this painfully slow reality? The answer resides in equations written by one man over a century ago. Albert Einstein published his theory of special relativity in 1905, and through those mathematical expressions, he constructed an invisible barrier that has confined humanity ever since. His revolutionary equations revealed something deeply troubling. Nothing possessing mass can ever reach or surpass the speed of light. Not now, not ever. The universe itself enforces this restriction through the very fabric of space and time. The underlying reason sounds deceptively straightforward on the surface. As physical objects accelerate progressively closer to light speed, they accumulate mass, and not just incrementally or gradually. The faster you travel, the heavier you become, and this relationship follows an exponential curve that climbs toward infinity. A spacecraft approaching light speed would eventually weigh more than entire galaxy clusters. Propelling it even 1 mile per hour faster would demand energy increases on astronomical scales. This creates an impossible catch-22 situation that cannot be resolved through conventional means. You require energy to accelerate mass through space, but the very act of accelerating causes that mass to increase exponentially, which demands even more energy, which increases the mass still further. The cycle spirals toward mathematical infinity precisely at the moment you would cross the light speed threshold. The universe essentially declares that you may approach this limit asymptotically, but you can never actually touch or exceed it. Einstein termed this phenomenon a universal speed limit, and for more than 100 years, his mathematics have withstood every challenge and experimental test thrown against them. Particle accelerators routinely smash subatomic particles together at velocities reaching 99.99% of light speed, and these experiments confirm Einstein's predictions with terrifying precision and consistency. Objects genuinely do gain mass as they accelerate. Time genuinely does flow at different rates. The rules appear to be absolutely fundamental and completely inviolable. Scientists have attempted every conceivable approach to discovering loopholes or workarounds in these restrictions. They have experimented with exotic propulsion concepts that push the boundaries of known physics. They have calculated intricate trajectories, exploiting gravitational assists from massive celestial bodies. They have proposed generation ships where entire civilizations would be born, live out their complete lives, and die during multi-millennial journeys between stars. None of these creative solutions changes the fundamental problem at its core. Einstein's equations lock the door to faster-than-light travel, and conventional physics appears incapable of finding any key that might open it. Physicists describe these laws as inviolable for excellent reasons. Break them carelessly, and you shatter causality itself. You generate paradoxes where effects manifest before their causes. You tear apart the logical framework that holds observable reality together in a coherent structure. The universe would seemingly rather collapse into chaos than permit any object possessing mass to exceed light speed. Time dilation compounds the difficulties even further. Even if you somehow manage to reach 99% of light speed through some miraculous technological breakthrough, time would flow at dramatically different rates for you compared to everyone remaining back home on Earth. A journey that subjectively feels like 10 years to you aboard the spacecraft might span many decades or even centuries for the civilization you left behind. You would eventually return home to discover that everyone you knew and loved had long since died, their great-grandchildren now elderly themselves, living in a world you barely recognize. The isolation becomes complete and absolute. Length contraction adds yet another twisted layer to this already strange situation. At these extreme velocities, space itself appears to compress directly in front of your moving vessel. Distances physically shrink from your reference frame. A trip that should theoretically require years might subjectively feel like mere months to you. Meanwhile, decades continue passing in the outside universe, The cosmos warps itself around fast-moving objects in ways that completely defy everyday common sense and intuition. For multiple generations spanning more than a century, physicists reluctantly accepted these limitations as the final word on the subject. Light speed represents the ultimate speed limit built into the fabric of reality. Nothing escapes it, nothing exceeds it, and nothing ever will. Teaching these principles became fundamental to every physics curriculum on Earth. Breaking the light speed barrier seemed as logically impossible as constructing a geometrically perfect square circle, or somehow making basic arithmetic yield results where 2 + 2 = 5. But a small number of scientists refused to accept permanent defeat in the face of these restrictions. They began asking a fundamentally different question that would eventually change everything. What if we have been conceptualizing movement itself in entirely the wrong way? Accelerating even a modest spacecraft to light speed demands more total energy than currently exists in every fuel tank, every battery, and every power generation plant on Earth when combined together. Then multiply that already incomprehensible amount by 1 billion, and you still fall dramatically short of the requirement. The mathematics underlying this nightmare scenario have been confirmed and verified repeatedly. As velocity increases, kinetic energy increases exponentially rather than linearly. Near light speed, energy requirements do not merely grow larger, they explode toward infinity. A spacecraft with a mass of just 1 metric ton would require approximately 9 × 10⁻16 power joules to reach light speed. That quantity equals the total annual energy output of human civilization across all sources, all of it consumed in mere seconds just to accelerate one relatively small vehicle. Nuclear fusion, the identical process that powers stars across the universe, offers our most energy-dense fuel source currently conceivable. Yet even converting the complete mass of a large asteroid into pure energy through matter-antimatter annihilation would barely budge a decent-sized starship to any meaningful fraction of light speed. We are not confronting difficult engineering problems that clever solutions might eventually overcome. We face fundamental impossibilities written into the operating code of reality itself. Project Daedalus, designed during the 1970 seconds by the British Interplanetary Society, proposed using controlled nuclear fusion rockets to reach 12% of light speed. The target sounds modest until you examine the actual design specifications. A spacecraft composed primarily of fuel storage tanks, the physical size of skyscrapers, carrying 50,000 metric tons of deuterium and helium-3 fusion fuel. The actual payload compartment designed to carry cargo and crew would be tiny by comparison, dwarfed by the massive fuel requirement. And that enormous ship would still require 2 full decades of continuous acceleration to reach merely the outer edges of our neighboring star systems. Antimatter propulsion systems could theoretically improve this mass ratio significantly. When ordinary matter encounters antimatter, they mutually annihilate with perfect efficiency, converting 100% of their combined mass directly into energy, according to Einstein's famous equation. It represents the single most efficient fuel theoretically possible under known physics. The insurmountable problem? We can only manufacture antimatter one individual particle at a time, using massive particle accelerators that consume enormous quantities of electrical power. And storing antimatter once created requires sophisticated magnetic containment bottles that themselves demand tremendous ongoing power to maintain. Producing sufficient antimatter to fuel even one interstellar mission would require thousands of years using current technological capabilities and production rates. Some physicists propose solar sails as an alternative approach, constructing giant reflective sheets that would be pushed forward by light pressure emanating from stars. These elegant systems require absolutely no fuel at all, just extraordinary patience. The acceleration is glacially slow, measured in tiny fractions of inches per second, gradually compounding over many years of continuous exposure. Reaching even 10% of light speed would demand decades of sustained acceleration. And the sail itself would need to span miles across its diameter, constructed impossibly thin yet somehow strong enough to avoid tearing apart under the accumulated stress. Every conventional propulsion method ultimately collides with identical fundamental barriers. The faster you wish to travel, the more fuel you must carry. The more fuel you carry, the heavier your spacecraft becomes. The heavier your spacecraft, the more energy you require to accelerate it to your target velocity. Engineers call this phenomenon diminishing returns. Poets might describe it as cosmic mockery of human ambition. Chemical rockets reach their performance ceiling around 5 miles per second. Ion drives might potentially achieve 20 or 30. Nuclear thermal engines could theoretically hit 50. Even the most optimistic fusion propulsion designs cap around 3,000 miles per second, which still represents merely 1% of light speed. We are throwing pebbles at a mountain, desperately hoping our efforts might somehow move it. The energy trap extends beyond simply building more powerful engines or discovering superior fuel sources. It represents a fundamental barrier written directly into the mathematical structure of reality itself. Einstein's field equations ensure that reaching light speed with any object possessing mass demands literally infinite energy. Infinite means genuinely impossible, not merely extraordinarily difficult. No amount of clever engineering, no breakthrough technology, no quantity of determination or willpower can alter that basic equation. Yet this trap only exists if you continue playing by the old rules of the game. What if movement itself is not what we think it is? What if there exists an entirely different way to cross vast distances? Earth might be approaching catastrophic environmental collapse, and we have nowhere else to go. That cold existential fact keeps researchers awake at night, because examining our cosmic neighborhood reveals a grim truth that cannot be ignored. Every other planet in our solar system qualifies as a hostile wasteland, completely incompatible with human life. Mars, our closest candidate for potential colonization, is a frozen desert where temperatures routinely plummet to -225 degrees Fahrenheit. Its atmosphere consists of 96% carbon dioxide and remains so thin that standing on the Martian surface equals being 19 miles high in Earth's atmosphere. Your blood would literally boil in the extremely low pressure. Massive dust storms engulf the entire planet for months at a time, and deadly radiation from space continuously blasts the unprotected surface because Mars lost its protective magnetic field billions of years ago. Venus appears even worse when examined closely. Beneath those beautiful thick clouds, the surface temperature reaches 860 degrees Fahrenheit, hot enough to melt solid lead. Atmospheric pressure there equals being 3,000 feet underwater on Earth, enough to instantly crush any unprotected human. The atmosphere itself consists mostly of carbon dioxide mixed with clouds composed of sulfuric acid. Robotic probes sent to Venus have survived less than 2 hours before being simultaneously crushed and melted. Living there is not difficult or challenging. It is flatly impossible with any foreseeable technology. The gas giants offer no solid surface to stand on whatsoever. Jupiter, Saturn, Uranus, and Neptune are essentially enormous spheres of hydrogen and helium, with crushing internal pressures and winds reaching 1,000 miles per hour. Their various moons present slightly better options in some cases, but remain frozen, airless, and immediately lethal to unprotected humans. Titan, Saturn's largest moon, possesses liquid methane lakes and a reasonably thick atmosphere. This sounds promising until you realize the surface temperature sits at -290 degrees Fahrenheit. You would freeze completely solid in seconds without extensive protection. Europa, orbiting Jupiter, might harbor liquid water beneath miles of ice covering its surface. But accessing that potential ocean would require drilling through a frozen shell in one of the most intense radiation-saturated environments in the entire solar system. Mercury swings between 800 degrees on its sun-facing side and -300 degrees in shadow. Earth's moon has no atmosphere, no liquid water, and faces the same radiation bombardment as Earth, but without any protective magnetic field to deflect it. Every single celestial body in our solar system is either far too hot, far too cold, far too radiation-soaked, or completely lacking the basic requirements for sustaining human life. Terraforming these worlds to make them habitable remains pure speculation and wishful thinking. Even the most wildly optimistic estimates suggest that making Mars barely habitable would consume thousands of years and require technologies we have not yet invented and may never invent. We would need to dramatically thicken its atmosphere, significantly warm its frozen surface, somehow restart its dead magnetic field, and create breathable air. Each individual step presents nearly insurmountable challenges that might prove genuinely impossible to overcome. Earth is not simply our home. It represents our only viable home for potentially millions of years into the future, even assuming unlimited technological advancement. That means if climate change, asteroid impacts, or any other catastrophe makes Earth uninhabitable, humanity has absolutely no backup plan whatsoever. We need to reach beyond our solar system boundaries. not merely for exploration or scientific curiosity, but for species survival itself. The critical problem remains that those potentially habitable worlds exist many light-years distant. Proxima Centauri b orbits within its star's habitable zone just 4 light-years away. The TRAPPIST-1 system contains 7 Earth-sized planets, 3 of them potentially habitable, located 39 light-years distant. Kepler 452b closely resembles Earth in many ways and sits 1,400 light-years away from us. These distant worlds represent potential future homes for humanity, but they might as well exist in another dimension entirely given current technology limitations. This is precisely why faster-than-light travel is not some luxury or frivolous dream. It represents an evolutionary necessity for species survival. We desperately need new worlds to inhabit, and reaching them demands breaking the most fundamental speed limit embedded in the structure of physics itself. Advanced telescopes have now identified over 5,000 confirmed planets orbiting distant stars, and dozens of these exoplanets sit squarely in the habitable zone where liquid water could theoretically exist on their surfaces. We can observe them through our instruments. We can measure their approximate size, estimate their composition, and calculate their orbital distance from their parent stars. We can determine their likely surface temperatures and make educated guesses about their atmospheric composition. We simply cannot reach them under any reasonable time frame. Proxima Centauri b haunts astronomers and exobiologists because it represents everything humanity desperately wants but cannot have. Located just 4.2 light-years away, this planet orbits a red dwarf star squarely within the habitable zone. It might possess liquid oceans covering its surface. It could potentially harbor primitive or even advanced life. Early observational data suggests it might even have a protective magnetic field, shielding it from harmful radiation. Scientists estimate it receives similar energy levels from its star as Earth receives from our Sun. The TRAPPIST-1 system discovered in 2017 sparked even greater excitement throughout the scientific community. 7 Earth-sized planets orbit a small, cool star, just 39 light-years distant. 3 of those planets sit squarely in the habitable zone, where conditions might support liquid water. Computer models suggest they could possess atmospheres, active weather systems, and stable climates conducive to life. Liquid water is not just theoretically possible on these worlds, but appears highly probable. Kepler 452b, nicknamed Earth's cousin by researchers, orbits a star remarkably similar to our own Sun. It receives only 10% more energy than Earth receives, suggesting surface temperatures falling in the right range for liquid water and potentially life. It sits 1,400 light-years distant, and discovering it felt like finding a twin sibling across an uncrossable ocean of space and time. These exoplanet discoveries continue multiplying year after year. Each observational campaign brings dozens of new candidates into focus. Planets with thick protective atmospheres, rocky worlds with day-night cycles similar to Earth, terrestrial planets with just the right mass to retain their atmospheres without crushing anything on the surface beneath impossible gravity. We have identified frozen worlds, molten lava worlds, ocean worlds completely covered in water, and desert worlds resembling massive versions of Mars. The galaxy absolutely teems with possibilities and potential. Yet every single one of these promising candidates remains completely unreachable within any reasonable time frame. Even Proxima Centauri b, our absolute closest candidate, would require 40,000 years to reach using current spacecraft velocities. TRAPPIST-1 would demand 600,000 years of continuous flight. Kepler 452b requires 25 million years. These numbers stop being travel times and transform into geological epochs spanning the rise and fall of entire civilizations. We remain trapped behind transparent windows, watching paradise we cannot enter or touch. Astronomers can confidently tell you the atmospheric composition of planets dozens of light-years distant, but we cannot send even a small robotic probe to investigate them in anything resembling a reasonable time frame. The James Webb Space Telescope can photograph the chemical signatures of water, vapor, and oxygen in alien atmospheres light-years away. Yet physically visiting those worlds to conduct detailed studies remains pure fantasy. The frustration extends far beyond scientific curiosity or academic interest. These distant planets represent potential homes for future human generations. They could serve as refuges if Earth becomes uninhabitable through natural or artificial catastrophe. They might harbor completely alien ecosystems we could study to revolutionize our understanding of biology. They could contain resources we might utilize. They might even host intelligent civilizations we could contact and learn from. Everything we desperately want to know, everything we urgently need to reach, sits tantalizingly just beyond our grasp, behind an insurmountable wall constructed from distance and immutable physics. Radio signals traveling at light speed would require years to reach these distant worlds. Even if we detected clear signs of intelligent life today and immediately sent a greeting message, their reply would not arrive until many decades later. A simple conversation would span multiple human generations from question to answer. Physical travel seems utterly impossible without completely reimagining how movement actually works at fundamental levels. Unless we stop trying to move through space and instead start moving space itself around us. Miguel Alcubierre was merely a graduate student, obsessed with Star Trek, when he decided to seriously calculate whether warp drive technology could actually function using real physics rather than fictional hand-waving. In 1994, he published a revolutionary paper that made professional physicists perform surprised double takes because his mathematics were not just creative science fiction. They were technically correct, according to established physics. The Alcubierre drive concept does not accelerate a spacecraft through space at all in the conventional sense. Instead, the mechanism creates a specialized bubble around the ship that actively warps the fabric of space itself. Space contracts sharply in front of the vessel, while simultaneously expanding behind it, creating a propulsive wave that carries the protective bubble forward through space-time. The ship inside remains completely stationary relative to the space immediately surrounding it, experiencing absolutely no acceleration forces whatsoever. Consider a surfer riding an ocean wave toward shore. The surfer is not swimming through the water or generating their own forward speed through muscle power. They are being carried effortlessly by the wave itself, standing essentially motionless on their board while the ocean does all the actual work of propulsion. Alcubierre's elegant equations described a spacecraft riding a wave through space-time in exactly this same manner. The brilliance emerges from exploiting a genuine loophole hidden within Einstein's field equations. Relativity explicitly states that nothing possessing mass can move through space faster than light. Accepted. But Einstein never claimed that space itself cannot move or expand faster than light. In fact, cosmologists know with certainty that space itself expands faster than light speed at the extreme edges of our observable universe. That rapid expansion is precisely how the universe grew from an infinitesimally tiny point to its current enormous size in just under 14 billion years. If space already routinely breaks the speed limit under natural conditions, why not deliberately harness that property for propulsion? Alcubierre's equations demonstrated you could theoretically create regions of negative energy density in front of a spacecraft, causing space to contract there, while simultaneously generating positive energy behind the vessel causes rapid expansion. The bubble containing the ship gets propelled forward by this deliberately asymmetric space-time distortion. No conventional thrust required, no crushing acceleration forces experienced. The ship simply rides the artificial wave you have created. His paper sent shockwaves rippling through the theoretical physics community worldwide. For the first time in history, someone had rigorously described a faster-than-light travel mechanism using completely accepted general relativity equations. This was not speculative science fiction or wishful fantasy. It represented peer-reviewed mathematics published in a completely legitimate physics journal. The proposed method appeared technically legal according to all known laws of physics as currently understood. Other scientists rushed to independently verify his calculations and check for errors. They discovered the mathematics held up under scrutiny. Space-time genuinely could be warped in this specific way without violating causality or contradicting relativity. The energy requirements remained absolutely astronomical and seemingly impossible to achieve, but crucially, they appeared technically finite rather than literally infinite. That represented a massive conceptual improvement over conventional propulsion, which demands literally infinite energy to reach light speed. The Alcubierre drive concept could theoretically achieve any velocity you desired. 10 times light speed, 100 times, 1,000 times, or even higher. The bubble itself is not actually moving through space in the conventional sense. So relativistic effects like time dilation and length contraction simply do not apply to objects inside. Crew members would experience completely normal time flow. They would not age slower than people remaining back home on Earth. They would not observe distances compressing ahead of them. Physics inside the protective bubble remains completely normal and familiar. Alcubierre himself later admitted he never genuinely expected the concept to work mathematically when he began his calculations. He was simply a physics student playing with equations inspired by his favorite science fiction television show. Yet his recreational calculation accidentally revealed a genuine possibility hidden within the deep mathematical structure of space-time itself. Reality appeared to contain a cheat code embedded in its fundamental operating system. Of course, actually constructing a functional warp drive presented complications that made the elegant theory look almost trivially easy by comparison. But the conceptual door stood open. The seemingly impossible suddenly looked merely extraordinarily difficult. Space-time is not empty, nothingness, or a void without properties. It constitutes an actual physical thing, a dynamic fabric that can bend, stretch, twist, compress, expand, and ripple in response to mass and energy. Every massive object creates a measurable depression in this fabric, like bowling balls sitting on a stretched rubber sheet. That depression or curvature is what we directly experience as the force of gravity. Einstein described this fundamental relationship over a century ago, and we have confirmed it through countless experiments and observations. GPS satellites must account for time flowing slightly faster in orbit than on Earth's surface, because they sit higher in the gravitational well created by our planet's mass. Experiments conducted with atomic clocks aboard airplanes demonstrate the identical effect with measurable precision. Black holes warp space-time so severely that nothing, not even light itself, can escape once you cross the event horizon boundary. The Alcubierre drive concept takes this established principle and weaponizes it for propulsion. Instead of passively letting gravity naturally warp space according to mass distribution, you actively and artificially create a bubble of dramatically warped space surrounding your spacecraft. The warp contracts space sharply in front of you while simultaneously expanding it behind you, generating a propulsive wave that pushes the bubble forward through space-time. Your ship never actually moves through space in the conventional sense. Space itself moves around the stationary ship. It sounds like mere semantics or word games until you realize this distinction sidesteps Einstein's speed limit completely and absolutely. Relativity restricts movement through space, but places absolutely no limits whatsoever on how rapidly space itself can move, compress, or expand. The distinction matters profoundly because all those nightmare side effects of near light speed travel, time dilation, length contraction, infinite energy requirements all vanish completely when you are not actually moving through space conventionally,